Okay. Going. There we go. Okay. Hello, friends, family, and random internet strangers, and welcome to week 4 of Let's Read Code. So, this week, a couple of chapters on two seemingly very disjoint topics. So, talking about binary codes and representing things with just ones and zeros, and then getting into mathy, logic-y stuff. So this is kind of the end of, we get into it a little bit more next week, but the end of learning new stuff. And after this, we're going to start more um, taking the stuff that we've already learned and putting it together and putting those things together with other things that are made out of things that we've been learning and starting to actually build towards making something that will actually start doing math or do computery things. So, start with chapter 9. Big concept here, going back to pretty much the very first chapter. You can represent pretty much anything with ones and zeros as long as you have enough of them. So, go through lots of different examples, starting with the simple, Paul Revere's lanterns in the American Revolution, going through movie ratings and how can we store those with ones and zeros, or letter grades, or uh, one of the, I kind of forgot how, what's the word I'm looking for? Out of touch, old fashioned something that some of these examples are. So, how rolls of film communicate to the cameras that they're in, you know, their properties, and how basically the equivalent of the ISO on your digital camera, how sensitive the sensor is. Well, this is how your film tells your camera how sensitive it is to light. And then we spent a lot of time talking about UPCs and barcodes, the little doohickeys printed on packaging at the store to tell the checkouts what exactly it is you're buying. So details of how all of those work aren't super important, but they do, the talking about it does introduce a couple of kind of important concepts. Starting with the idea of signal and noise. So if your signal is the information that you're actually sending, noise is the random-ish external interference that messes with your signal, right? So we can talk about this in a lot of different contexts, even like two people sitting next to each other and talking, right? Because you're talking, you're making noise, not noise. You're producing audio signal that is carrying information to your conversation partner. The environment is just full of noise, right? Birds and bugs and wind and branches rustling and all that kind of stuff. But it's relatively quiet compared to the person talking who's sitting right next to you. So your signal to noise ratio, or how strong your signal is compared to all the background noise, is pretty high. So it's pretty easy to hear what's going on, understand what the person's saying. Whereas if you're, in the middle of the pits at a robotics competition or at a rock concert or whatever other loud places you might go, the noise is a lot louder. There's a lot more of it. So in order to get your message across, you either have to be a lot closer to the person you're talking to or talk a lot louder so that your signal to noise ratio goes up and you can actually be understood. Other big important concepts, communication and code wise, UPCs, part of the reason they spent so much time talking about UPCs is getting across the idea of redundancy and how that works, to help ensure that your message actually gets across. So if you go back and look at how the UPCs work, the actual information, like the actual number that it's sending, is actually encoded in that barcode twice. And then the way it's encoded is not necessarily the most efficient way. Like each individual digit in the number is stored as what, 7 bars. So we go back and think about, okay, there are 10 digits. How many binary digits do we need to be able to actually store 10 things? Anybody remember? Anybody want to do the math real quick? No. So we need 4 binary digits to store an individual like 0 through 9 digit, right? 2 to the 4th is 16, which is the lowest power of 2, larger than 10. But we're using 7 bits here, or 7 bars, so that we have a little bit of extra room, so that when the barcode scanner actually scans the code, there's a little bit of room for error in there, because the thing may not be printed just absolutely perfectly. So there's a little bit more wiggle room in what it's reading, or so it can immediately tell that something's not quite right and reject the read or try and read it again. So that's the big important parts of chapter 9. Not a whole lot necessarily going towards how we build computers, but again, sort of reinforcing that idea of we can represent pretty much anything we want with ones and zeros, and what those ones and zeros mean are very up to whoever's sitting here interpreting that information. So, any questions about any of that? No? Great. So, moving on, chapter 10, where things start getting mathy and logicy. So, a lot of this is more like background information. It's not necessarily helping us actually go build a computer, except towards the end. But it's still kind of interesting to think about and learn how some of this stuff built up to where we are now. So start off talking about this thing called propositional logic, which is a thing the book never actually, or a word the book never actually uses. Basically the formal study of true and not true things, or cause and effect, or that kind of thing. So talk about syllogisms, which are just little, not quite logic puzzles, but logic statements in a sense. So another example here, if it's raining, then it's cloudy. So if it's raining, it must be cloudy, right? And then we can do lots of different transformations on that statement to say, okay, it's cloudy, so it might be raining. Or it's not cloudy, therefore it must not be raining. So if you go actually study computer science or philosophy or certain branches of math, like you will literally take a class about all of this stuff. So George Boole, talked a bit about him in here. He's the guy who sort of figured out a way to represent this logic stuff in a more mathematical form. So spends a lot of time talking about Boolean algebra and sort of doing math with whether things are true or false, or whether things belong to certain groups or not. We don't really spend a whole lot of time these days talking about it quite like that. So I'm going to dive in a little bit deeper and explain a little bit more about the part that it very briefly glazed over, about how we actually talk about this stuff. So the book talks about writing things like A plus B equals 1, right? So we have some condition A, the plus sign, basically equivalent to saying or something, right? So we have condition A or condition B is a true statement if either of these things are true, right? So that's not usually how we write these things because it gets confusing trying to use the same symbols for things that don't necessarily exactly correspond to each other. So talk about A and B, A or B. So these are the four sort of primitive Boolean logic operations that we're going to be talking about. So as we talked about in the reading, talked about these two and also that one a decent amount. So I'm going to spend a second. I think there's an actual erase everything button somewhere, but I couldn't find it. So I'm going to talk about A and B. So A and B are both two things that are either true or false. So we can talk about A being true or false and B being true or false. So A and B implies that the result is only true if both things are true. Or in this case, since we're talking about ones and zeros, A and B is 1 only if both A and B are 1. So we get 1. So this little thing right here is what we call a truth table. We'll be looking at those quite a bit. We start looking into more complicated circuits because we can basically plug in any number of propositional variables here, like A or B. It's raining, it's cloudy outside, that kind of thing. And based on the circuit or based on the mathematical formula we're looking at, show what the results are for different combinations of inputs. So I can also do the same thing for A or B. So A or B implies that the result is true if either or both of them are true. So if A is true and B is true, we get true. If A is true and B is false, still get true. If B is true and A is false, still get true. If neither of them are true, we get false. Make sense so far? Okay. So one that the book didn't talk about, but is still fairly important and useful. XOR, exclusive OR. So this one is only true if exactly one of the inputs is true. So it's like exclusively or, not and, right? And then the last one, just a one-dimensional thing. Not something just means we get the opposite of whatever we fed into it. So let's try a couple of examples here. So I'm going to make a quick little formula here. So just like we talked about in the book, the cat selection formula of, great, here are the criteria you want for the cat you're going to adopt. Here it is reduced down to a Boolean algebra formula, and then eventually we go turn that into a circuit. So run through a couple of simple ones of those real quick. So let's say we have P something like that. P and Q or M. So P. So if we say that P is true, Q is false, and M is false, is the final result of this thing true or false? True or false? I see one answer, two answers. It appears that they are correct. The answer is false, because if we go put these in, true, false, false, true and false is false, or false gives us a final answer of false or 0. What about 1? What's the answer now? I see trues everywhere, which is good because that is the correct answer. 0, 1, 0, and 1 is 0, 0, or 1 is 1. Okay. So kind of got the idea there. So now I'm going to try something here real quick. So I said last week, we're going to be using 2 different pieces of software to explore how some of this works and play around with circuits in real time, because it gets annoying to actually sit here and build some of these things. So we're going to go play Minecraft here for a bit. Okay. So I'm playing with a handful of mods in my Minecraft install to make things a lot more fun to play with. The big important one that I'm using is called Project Red. It adds a whole bunch of wiring and other handy things that make playing with this digital electronics simulation-y stuff a whole lot more fun, because doing it with the just plain old redstone stuff that comes with vanilla Minecraft is kind of painful and gross. So got some wire. Other really cool thing is it comes with colored wire, so you can run different wire paths right next to each other and they don't interfere with each other, which is great. So over here, I have built the cat selection circuit from out of the book, so we can actually put it together and watch it work. Unfortunately, there are no good just like switches in here to play with, so I'm just going to go put wire in places when you've flipped the switch. So right now we have no cat in the system. None of the switches are triggered. So when I go turn the power on, the signal never goes anywhere, and so the light at the end doesn't light up because we don't have a cat that matches our criteria. However, if I say we have a black male cat, I'm going to go put some wire here in the black part and go find male part. and also the not white part, because black is in fact not white, and go turn it on, we see, hey, the light at the end of the thing has lit up. And we can actually go see inside the circuit where it's lit up and where it's not. So because the cat is black, we remember from the book, what is the actual conditions we were given here? Where'd it go? Okay, there it is. So we want a male neutered either white or tan cat, or a female neutered not white cat, or a black cat. So I filled in the black part of the circuit here. So that means the electricity has a path from our battery or our power source or whatever through this branch of the circuit and straight through to the end. Whereas if I try to go this way, it is a male cat, so the female switch doesn't get flipped, so there's no place for the electricity to flow through here, so it stops. Come down here, the male cat, but it's not neutered, so the switch doesn't get closed and the circuit stops there. So laying it out like this makes it pretty easy to actually see the flow of the circuit and how it's all coming together and whether the light is turning on or not before we even hit the switch. So, any questions with any of this so far? No? I see lots of heads shaking. Okay. So, let's go break this thing down. I really should have built like some water behind a piston that would instantly clear all of this stuff out. That would have been a good idea. Okay. We'll need signs. So let's think of another example we could run through with this. Let's go shopping for food. That sounds like a reasonable answer. And also, I need to go grocery shopping later. So, sure. So, I want to evaluate whether I want to buy something. So, conditions that might be in place. Okay, so let's work off of 3 different conditions here. Whether it's animal-based, whether it has nuts, or whether it has dairy ingredients in it. So let's say I have no allergies or aversions to food of any sort. What kind of circuit am I going to build here? I know, you may have to actually talk to answer this one.
A complete one.
So if I don't care about any of those things, I'm just going to build a circuit straight through, because no matter what I'm checking against, it's always going to pass, right? So what if I am allergic to nuts. Sad. Okay. So I'm going to get rid of these. Oops. So if I'm allergic to nuts, I don't want to buy anything that has nuts in it. So I'm going to make a new switch here called doesn't contain nuts. So if I'm buying something that has no nuts in it, this switch will get flipped. There's something there to complete the circuit. So when I turn it on, the light lights up. If the wire is gone, if something has nuts in it, I turn the circuit on. The circuit has no complete path back to the light, doesn't work. Let's say I'm buying something for a robotics event where I have people who have all three of those restrictions in place, but not necessarily any one person having all three of those restrictions. So I need something that is not animal-based or sad. Doesn't have nuts or so for this, we just want, basically, this is all one big OR. It's a three-way OR statement, right? Because as long as any one of these things are true, then the circuit or the grocery item passes our test, and we can put it in our shopping cart. So the thing here. So I'm gonna go buy some fruit. So not animal-based, doesn't have nuts, doesn't contain dairy. I turn it on and the light lights up because again, it's meeting at least one of our conditions. So let's say I'm buying, I don't know, some sort of nut-based jerky product. I don't know, but doesn't contain dairy, has nuts, has meat in it. So one of the branches is still complete, so the light still lights up. So that all makes sense? Cool.
Yep.
So that is it for this week as far as content goes. Next week, we're going to use this to start doing very, very small amounts of math and also learn how to build slightly more complicated circuits to make things a little bit less gross and wiry. And play more Minecraft, because we can. So, any other questions, comments, concerns? Did you learn anything cool or interesting? I see head shaking. Great. Good job. I feel like I've accomplished my goal. All right, then. So, for next week, read the next 3 chapters. I would highly, highly, highly recommend actually sitting down and working through some of the stuff. We're going to be talking about doing math with binary. And if you just try and read it and understand what's going on, it's going to make very little sense, because especially the last chapter, chapter 13, I think it is, where you start talking about subtraction. The way computers do subtraction is a little bit unintuitive. So actually sit down and try it for yourself, and it will make at least a little bit more sense. Cool. Cool. So I will see you all next week.